Ever since the discovery of the bizarre behavior of quantum systems, we've been forced to reckon with a seemingly uncomfortable truth. For whatever reason, it appears that what we perceive of as reality, where objects are and what properties they possess, isn't itself fundamentally determined. As long as you don't measure or interact with your quantum system, it exists in an indeterminate state. We can only speak of the properties it possesses and the outcomes of any potential measurements in a statistical, probabilistic sense. But is that a fundamental limitation of nature, where there exists an inherent indeterminism until a measurement is made or a quantum interaction occurs? Or could there be a hidden reality that's completely predictable, understandable, and deterministic underlying what we see? Reality is a complicated thing, especially when it comes to quantum phenomena. Let's start with the most famous example of quantum indeterminism, which is the Heisenberg Uncertainty Principle. The Heisenberg Uncertainty Principle tells us that there are pairs of properties, like position and momentum, that cannot both be known to arbitrary precision simultaneously. The more precisely you know one, the less precisely you can know the other. In the classical macroscopic world, there's no such thing as a measurement problem. If you take any object that you like, a jet, a car, a tennis ball, a pebble, or even a mote of dust, you can not only measure any of its properties that you want to, but based on the laws of physics that we know, we can extrapolate what those properties will be arbitrarily far into the future. All of Newton's, Einstein's, and Maxwell's equations are fully deterministic. If you can tell me the locations and motions of every particle in your system or even your universe, I can tell you precisely where they will be and how they'll be moving at any point in the future. The only uncertainties we'll have are set by the limits of the equipment we're using to take our measurements. But in the quantum world, this is no longer true. There is an inherent uncertainty to how well, simultaneously, you can know a wide variety of properties together. If you try to measure, for example, a particle's position and momentum, energy and lifetime, spin in any two perpendicular directions, or its angular position and angular momentum, you'll find that there's a limit to how well you can simultaneously know both quantities. The product of both of them can be no smaller than some fundamental value, proportional to Planck's constant. In fact, the instant you measure one such quantity to a very fine precision, the uncertainty in the other, complementary one, will spontaneously increase so that the product is always greater than a specific value. Quantum particles like electrons, protons, and atomic nuclei have an angular momentum inherent to them, something we call quantum spin, even though nothing is actually physically spinning about these particles. In the simplest case, these particles have a spin of half, which can be oriented either positive or negative in whatever direction you measure it. Now here's where it gets bizarre. Let's say you shoot these particles. In the original, they use silver atoms through a magnetic field oriented in a certain direction. Half of the particles will get deflected in one direction, which is positive, and half get deflected in the other, which is negative. But if you pass them through a magnetic field oriented perpendicular to the first, they'll split once again in the positive and negative directions, as though there was still this uncertainty in which ones were positive and which ones were negative in this new direction. And now, if you go back to the original direction and apply another magnetic field, they'll go back to splitting in the positive and negative directions again. Somehow, measuring their spins in the perpendicular direction didn't just determine those spins, but somehow destroyed the information you previously knew about the original splitting direction. The way we conceive of this traditionally is to recognize that there's an inherent indeterminism to the quantum world that can never be completely eliminated. When you exactly determine the spin of your particle in one dimension, the corresponding uncertainty in the perpendicular dimensions must become infinitely large to compensate. Otherwise, Heisenberg's inequality would be violated. There's no cheating the uncertainty principle. You can only obtain meaningful knowledge about the actual outcome of your system through measurements. But there has long been an alternative thought as to what's going on, the idea of hidden variables. In a hidden variables scenario, the universe really is deterministic, and quanta have intrinsic properties that would enable us to predict precisely where they'd end up and what the outcome of any quantum experiment would be in advance. But some of the variables that govern the behavior of this system cannot be measured by us in our present reality. If we could, we'd understand that this indeterminate behavior that we observe is merely our own ignorance of what's truly going on, but that if we could find, identify, and understand the behavior of these variables that truly underlie reality, the quantum universe wouldn't appear so mysterious after all. And this brings us to one of the most intriguing phenomena in quantum mechanics: quantum entanglement. Imagine two particles that are entangled, meaning their states are deeply interconnected no matter how far apart they are in the universe. If you measure the state of one particle, the state of the other particle is instantly determined, even if they are light years apart. This spooky action at a distance, as Einstein called it, defies our classical understanding of space and time. Consider this. You have two entangled particles, and you send one to the other side of the galaxy. The moment you measure the spin of the particle on Earth, the spin of the particle on the other side of the galaxy is instantly known. If all you can see are the grains of sand, it will look to you as though each individual one vibrates with a certain amount of inherent randomness to it, and that large-scale patterns or correlations might even exist between grains of sand. However, because you cannot observe or measure the vibrating plate beneath the grains, you cannot know the full set of dynamics that govern the system. Your knowledge is the thing that's incomplete, and what appears to be random actually has an underlying explanation, albeit one that we do not fully understand. This is a fun idea to explore, but like all things in our physical universe, we must always confront our ideas with measurements, experiments, and observations from within our material universe. One such experiment, in my opinion the most important experiment in all of quantum physics, is the double-slit experiment. When you take even a single quantum particle and fire it at a double slit, you can measure, on a background screen, where that particle lands. If you do this over time, hundreds, thousands, or even millions of times, you'll eventually be able to see what the pattern that emerges looks like. Here's where it gets weird though. If you don't measure which of the two slits the particle goes through, you get an interference pattern. Spots where the particle is very likely to land, and spots in between where the particle is very unlikely to land. Even if you send these particles through one at a time, the interference effect still persists, as though each particle were interfering with itself. But if you do measure which slit each particle goes through, such as with a photon counter, a flag, or via any other mechanism, that interference pattern doesn't show up. Instead, you just see two clumps, one corresponding to the particles that went through the first slit, and the other corresponding to those that went through the second. And if we want to try and pin down what's actually going on in the universe even further, we can perform another type of experiment, a delayed choice quantum experiment. These experiments allow us to decide whether to measure the path of the particles or not after they have already passed through the slits but before they hit the screen. Astonishingly, the choice to measure or not can retroactively change the outcome, forcing us to rethink our understanding of time and causality. Next of the most perplexing aspects of quantum mechanics is the measurement problem. This puzzle was famously illustrated by Erwin Schrödinger in 1935 through his thought experiment known as Schrödinger's cat. Imagine a cat placed in a sealed box along with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the Geiger counter detects radiation, the hammer shatters the vial, releasing the poison and killing the cat. If no radiation is detected, the cat lives. According to quantum mechanics, until we open the box and observe the cat, it exists in a superposition of states, both alive and dead simultaneously. In recent years, various interpretations have been proposed to address the measurement problem. The Copenhagen interpretation, for instance, suggests that the wave function collapses upon measurement, while the many worlds interpretation posits that all possible outcomes occur in parallel universes. Regardless of which interpretation you find most compelling, one thing is clear. The quantum measurement problem remains one of the greatest mysteries in physics. In physics, we have this idea of locality, that no signals can propagate faster than the speed of light, and that information can only be exchanged between two quanta at the speed of light or below. What Bell first showed was that, if you want to formulate a hidden variable theory of quantum mechanics that agreed with all of the experiments we've performed, that theory must be inherently non-local, and some information must be exchanged at speeds greater than the speed of light. Because of our experience with signals only being transmitted at finite speeds, it's not so hard to accept that if we demand a hidden variables theory of quantum mechanics, locality is something we have to give up. Well, what about the Kochen-Specker Theorem, which came along just a few years after the original Bell's theory? It states that you don't just have to give up locality, but you have to give up what's called quantum non-contextuality. In simple terms, it means that any experiment you perform that gives you a measured value for any quantum property of your system is not simply revealing pre-existing values that were already determined in advance. Instead, when you measure a quantum observable, the values you obtain are dependent on what we call the measurement context, which means the other observables that are measured simultaneously along with the one you're specifically after. The Kochen-Specker Theorem was the first indication that quantum contextuality, that the measurement result of any observables depends on all the other observables within the system, is an inherent feature of quantum mechanics. In other words, you cannot assign values to the underlying physical quantities that are revealed by quantum experiments without destroying the relationships between them that are essential to the functioning of the quantum universe. The thing we always have to remember when it comes to the physical universe is that no matter how certain we are of our logical reasoning and our mathematical soundness, the ultimate arbiter of reality comes in the form of experimental results. When you take the experiments that we've performed and try to deduce the rules that govern them, you must obtain a self-consistent framework. If you wish to impose an additional underlying set of hidden variables that truly governs reality, there's nothing preventing you from postulating their existence. What the Kochen-Specker Theorem tells us, though, is that if those variables do exist, they do not predetermine the values revealed by experimental outcomes independently of the quantum rules we already know. This realization, known as quantum contextuality, is now a rich area of research in the field of quantum foundations,